Okay, so 5-4. 5-4 is about more about integration. You are going to find that this section particularly isn't going to be much different than what we've done before. The main thing I think that you're going to notice is there are some tips and tricks in this section that we didn't do before. Other than that, you won't find too much different in 5-4. 5-5 gets a little bit funky. We will spend a little more time on 5-5 than 5-4. These formulas, I believe these formulas are all written down in your paper already. Basically, they're just reminding you that for a constant, you can bring it out in front. If there are two individual pieces, you can add them individually or subtract them. Here is the reverse for your power rule. Here, if there's a constant, you have to tack on an x. If you reverse a sign, don't forget the negative. If you reverse a cosine, you don't need a negative. Here's the reverse of a tangent, your secant squared. Cosecant squared is the one that gets a negative on it. Here is reversing secant tangent goes back to secant. Reversing cosecant and cotangent goes back to a negative cosecant. So those are nothing new. If you want to take a little screenshot so you have it, let's just practice some of these one more time, okay? So if we look at this integration from 1 to 4 of the square root of t times 1 plus t, I would suggest do what we did for derivatives. If we are going to do that, I would rewrite that as a t to the 1/2. We don't know any sort of power rule at this time, so you have to distribute that in. Do the necessary rewrites before you do your antiderivative. So I would suggest as you do this problem, it's impossible. We do not know a way to do the antiderivative, but this rewrite allows us to do that. If we do the antiderivative, remember the t to the 1/2 becomes a t to the 3/2, but we have to divide by 3/2, which throws that reciprocal out in front. T to the 3/2 becomes a 5/2, but we have to throw that reciprocal out in front. And then put your little boundaries there to remind you that you have to put in your boundaries. Our boundaries would be upper bounds of 4 and lower bounds of 1. Remember, it's always upper bound, stick that in, minus lower bound, stick that in. Remember, this is a square root. Do the square root before you cube it. Do the square root before you fifth it. Okay. So if I stick in 4, I get 2/3 4 to the 3/2 plus 2/5 4 to the 5/2 minus, and put in parentheses your lower bound. So it's 2/3 times 1 and 2/5 times 1. Anything, 1 to any power is always just 1. Now let's analyze this piece for a minute. This tells me to take the square root first. The square root of 4 is 2. 2 to the 3rd power is 8. 8 times 2 is 16. So make that 16/3. Now I'm going to do the same trick here. That would be 2 to the 5th power, or 32 times 2 is 64 to the 5ths. Minus 2/3 and minus 2/5. So I'm going to put the thirds together and the fifths together just so that I don't have to pull out a calculator right at the moment. That's 14/3 plus 62/3, or 62/5, I'm sorry. So I just combine the thirds and combine the fifths. Now, in order to do that, I want the exact answer. I don't want fractions, decimals. I want the fractional equivalents. Keep it fractions. If you multiply 14 by 5, you get 70/15. but 62 we need to multiply by 3. So that's 186 fifteenths for a total of 256 fifteenths, which I don't believe reduces down. And if I did anything funky, please tell me. No, that doesn't reduce, so just leave it. Okay? So that's just reminding you that any radicals rewrite as a fractional exponent. Do everything you can for the rewrites that you would do for a derivative. Do that same rewrite for an antiderivative. So that's the main takeaway there. Okay. Now here are some information about some applications of integration. If we have a rate of change, so miles per hour, let's just go miles per hour for a minute. Let's say that this big F prime is a rate of change. So let's go, it's a miles per hour. If we go backwards, then this is just the change in miles from B to A. So if it's a rate and it goes backwards, you take the time part off and it just becomes a net change in the function from A to B. So miles per hour would become just miles. Feet per second would just become feet. Volume, think about our related rates problems. Volume per unit of time would just become volume. The net change in volume. So if you are integrating some kind of function, and I'll give you an example, and let's say that is the change in volume per unit of time, then the answer would be the actual net change in volume. So it actually goes, if this is a let's go cubic meter per second, so maybe water is flowing into something, then this is just going to be the meters per second, the change in meters at that point. So that's why there's so many applications of derivatives, because when you go backwards, you can find how something has changed over that particular time span. So you will find there will be some applications to this stuff. And we already kind of saw how to go from backwards, that our velocity gave a position. And that's one example of the net change theorem. Do you have everything right there? So net displacement, let's look at our first example here. It says, given a velocity function for a particle in motion from time 0 to time 3, find the net displacement of the particle. How much has the particle changed in movement, the net displacement from time 0 to time 3? Well, all we have to do, if we integrate something that is in meters per second, our answer is going to be the net change in meters. And that's directly related to the fact that our antiderivative of a velocity is a position. So then let's go ahead and just integrate that. So that's going to become 3t squared over 2 minus 5t evaluated from 0 to 3. Excuse me. If I stick in 3, I get 27 halves minus 15. If I stick in 0, I get 0. So it's just 27 halves minus 30 halves, which is negative 3 halves. So what does that that negative mean? That negative tells us that we have gone backwards during that time frame. So we have lost 3.5 meters. So that's kind of what that tells you. Any questions about that one? Okay. So let's look at this one. So it says to find the total distance traveled of a particle according to the velocity function in meters per second over a time interval from 0 to 3. See how it says total distance? That's going to be different because total distance is not net. That last one told us that after it was all said and done, we lost, what was it, negative 1.5 meters, okay? But let's take a look at something that we know about that function, okay? So let's think about the graph for a moment. 3t minus 5 equals 0 at 5/3. 5/3 is about 1.7. If you were to graph it from 0 to 3, at 0, we're at negative 5. At 3, we are at 4. The negative answer to that integration in example 5.24 told us that when it was all said and done, we lost some distance. We went backwards. But this particle went backwards and then went forward a little bit. So if we wanted to look at the net area, technically, it is the absolute value of 3t minus 5. Because we want it all to be expressed as positives. So this is what you have to do. From 0 to 5/3, it is the opposite of what we started with. But from 5/3 to 3, it's a positive. So it is what we started with exactly. So we have to break it up into negatives and positives. So because of the fact that part of it was under, we're traveling backwards at that point. But we're still traveling. So if they asked how far did the particle actually travel, what was the total distance? You got to think about, okay, it's going backwards here and then going forward here. That's why we have to split it up at that spot. Okay, so from 0 to 5/3, we are really integrating the opposite of what we had. So negative 3t plus 5. But from 5/3 to 3, you don't have to do that. No, this one, I'm sorry, I didn't. My parenthesis was in the way. I distributed the negative in there. Okay. Okay, so if we integrate, we're going to get negative 3t squared over 2 plus 5t from 0 to 5/3. And then this one, I get positive 3t squared over 2 minus 5t from 5/3 to 3. Because that would be the net area, okay? So if you stick in 5/3, you're just going to have to trust me a little bit. But if you stick in 5/3, you get, oh shoot, okay, so you get negative, okay, so that's going to be 20, you get 25 over 6 plus 25 over 3 minus 0. And then if we stick in 3, we get 27 halves minus 15 minus, if we stick in 5/3, which I've already done once, that would be 25 over 6. And then that should be minus 25/3. Okay, now distribute this negative here. That should be our only thing to distribute. So we get negative 25/6 plus 25/3 plus 27 halves minus 15 minus 25/6 plus 25/3. Let's just make sure I got all the same things they did. Yep, okay. And this will never, or should be, if you broke it up right, you should always, when you're doing this, get a positive answer. And the answer is 41/6 meters. So in the first problem, we netted negative 1.5 meters. So we lost negative 1.5 meters. But if we look at what actually happened, I traveled backwards this amount. I traveled forward this amount for a total of 41/6 meters, which is I don't know what is 41 divided by 6 point something meters total. Okay. So watch how they ask the question. If they say, what is the net change in distance, or your final distance change, you would have to do what you did in 524. If they asked you, what is your total distance that you traveled, you have to look at where the integration would be negative and where it would be positive. Okay. So that's the main thing there. Okay, so let's look at this problem. It says if the motor on a motorboat is started at t = 0 and it consumes 5 minus t cubed gallons per hour for the first hour, how much gasoline is used in that first hour? So that is from 0 to 1. We're going to integrate the gallons per hour, and then we're going to just get gallons. Well, if we integrate that, we get 5t minus t to the 4th over 4 from 0 to 1. If we plug in 1, we get 5 minus 1/4. If we plug in 0, we get 0. 5 is 20/4, so 20/4 minus 1/4 is 19/4 of a gallon. So if we were thinking as far as decimals, that is 4.75 gallons. So that is an application problem. So it's kind of interesting that if I know the rate of change and I integrate it, then I will just get that top, in this case, gallons. So if you're integrating over time, the time goes away, and then you're just left with the gallons. Okay. Remember, our derivative was a rate of change. So our antiderivative would just be that thing. And so that's the difference. Now, some things to think about. If a function is even, so this first case is if a function is even, it has y-axis symmetry. So if we looked at its picture, a perfect example is f of x equals x squared. F of x equals x squared is an even problem. If I am integrating from -1 to 1 of f of x equals x squared, that is the same as 2 times the integral from 0 to 1. Now let's think about why that's the case. The area here and the area here, because of the symmetry of an even function, will be exactly the same. So if you know that it is an even function, you are welcome to do this, but usually isn't, we've seen a lot of times, not every time, but plugging 0 in is pretty nice. So all that allows us to do is to double the area here to get the total area from left to right, okay? Another function that's odd, let's say our cubic function. I'll draw that on the graph paper since I actually provided some graph paper. Maybe I'll draw it on the graph paper. Oh, did I? How nice of me. Let's say that we go from -1 to 1 of x cubed. That function looks like that. The area here is the exact shape of the area on the other side, but this one is negative and this one is positive. So an odd function, if these are equidistant from 0, the area, the net change will always be 0. So if you recognize that you have an odd function, it's even easier if this goes from -a to +a. So it has to be equidistant from the center, from 0. These two will always cancel each other out. You always get an answer of 0. So all this provides, you never have to use this rule. It would always work itself out. What this rule does is this rule just is a little shortcut. It does allow you, if you recognize that it's even, you can split it up and just do 2 times the integral from 0 to that a value. If it's odd, you're going to get an answer of 0 because the areas will cancel each other out. And I totally didn't draw this right. That's not the area that I wanted. This is the area I wanted. Like, why does that look so funky? There we go. That's better. Like, those don't match. Anyway, so that's just a little shortcut again. You don't have to use it. It's helpful, but it's not necessary. Reminder of our trig functions. Cosine is even. Sine and tangent are odd. So sine and tangent might have that nice cancellation and get you 0. Cosine is not. Cosine is our only original 3 trig functions that is even. So just so you know how our trig functions work. Way to remember that, odd functions go through the origin. Sine and tangent go through the origin. Cosine isn't. It doesn't go through the origin. It has a perfect split down the y-axis. So if that helps you remember that cosine is even, but sine and tangent are odd. So let's take a look at this function we see here. Now they gave us a little hint here that this was an even function. It says to integrate from -2 to +2 of this even function. So let's do it this way, just using our rules. And I'm going to prove to you that since it was even, we could have also do this. we can split it up from 0 to 2 and just double the area we find. Because we could fold it across the y-axis, we'll get the same area to the left of 0 that we get to the right of 0. So let's start out with the top one. Think about our integration rules. We are going to go from antiderivative 3x to the 9th over 9 minus 2x from -2 to +2. If we plug in 2, we get, I don't know what 2 to the 9th is off the top of my head, 512 over 3 minus 4 minus, if we plug in -2, we get -512 over 3 plus 4. And then when we distribute that in, look what happens. We get 5/12 minus 4 plus 5/12 minus 4. You see how these two things are a perfect match. We got double the area on both sides of 0. And so we get 1,000 thirds. Anyway, now let's do it the bottom, and I'll show you that we're going to get the same answer. So that would be 2 times 3x to the 9th over 9 minus 2x from 0 to 2. If I plug in 2, I get 5/12 minus 4. If I plug in 0, I get 0. I still get 1,000 over 3. Now, why is that? If we look at the graph, don't expect this graph to be to scale. If we look at our graph from -2 to +2, I don't know where it hits. I mean, I guess I could figure it out. 2, 3 times 2 to the 8th. It's just going to be so giant. That's 766. I don't know. But anyway, the area here and the area here are perfect duplicates of each other. And so that's why you are welcome to split it down the middle, calculate this area, and then just double it. Now, you'll see it's not much different one way or the other. So if you decide and you just look at it and you do the first way, go for it. But if you do recognize that it's an even function, you don't have to. You could do it this way. So both get you the same thing. It's really if you just happen to recognize that fact. The one that it's helpful to is for an odd function. So one, these two have to be opposites of each other. So if we integrate from -pi to pi of the odd function -5 sine of x, the answer is 0. Now, let's just verify that it really, really is, okay? So the antiderivative of -5 sine of x is +5 cosine of x. The cosine of pi is -1, so that would be -5. The cosine of -pi is -1, so that's -5. So that's -5 plus 5, or 0. Now, if right off the bat you recognize the fact that these are perfect opposites and this is an odd function, You know it's going to be 0? Fine. If not, the actual integration will work itself out. The rules of even and odd. Let me remind you those rules. If you plug in a negative for an even function, it should go away. It shouldn't have any effect on the problem. For an odd function, if you plug in a negative, it is the opposite of the original. So that's a way we can tell. If you plug a negative into the sign, it pops it out and it does become the opposite. So -5 sine of negative x is +5 sine of x. Not that it matters, but anyway. So if you recognize if it's even, you can double the area if the boundaries are opposites. If the boundaries are opposites and it's odd, your answer will always be 0. Now that's not, net versus total. Be careful. But there you go. Okay. Yeah. Here, wait, I'm sorry. I kind of got that cut off if you want to do it again. So then your homework is what you see here. Tomorrow we are going to take notes for 5-5. So please use the rest of the time to actually try some of these, and I'll go over if you happen to have any questions.